So imagine you have a survival analysis data set. For example, you have the lifetime of a machine. The first thing you would try is to model to fit the most well-known distributions such as Pareto, Weibull, Gamma. And if those models do not adjust very well to your data set, then you would try those distributions whose name nobody knows. For example, I don't know if you have heard, well, some of you may have heard of the Coomaraswamy Weibull. The thing is that every year a new distribution is introduced in the literature. And if you try to look for citations for this paper, you cannot find a applied paper. So it's very common to see distributions that are introduced and never seen again. So what we did in this work here is just collect some distributions and try to work on them, try to see what happens when we try to do inference. For example, Bayesian inference or frequentist inference. So in this slide here I have some examples such as the inverse Rayleigh, generalized exponential, beta exponential, and the Kuhn-Weibull. So basically I'm going to implement some Bayesian models here, some inferential Bayesian models on survival analysis distributions. This is a joint work with Danilo Roges and Adriano Polpo. This is a work in progress. I'm just going to go through some distributions that were introduced in recent papers, or not so recent papers, explain a little about our Bayesian analysis implementation, and then discuss some results here. So the most simple method to create a new distribution is just to make a transformation on a distribution that we already know. So for example, if we are working with survival analysis distributions, we are worried about random variables that are greater than 1, that have support on the positive numbers. And if you just take the inverse of that random variable, you will still have a variable that's greater than 1. And maybe that this was the first method to find new distributions. You can just work here on the change of variables in the density function, and you will get a new distribution and a new class of PDFs. So we have some old papers here that apply this transformation to get new distributions. For example, we can find the inverse Rayleigh. It was introduced in 1964, and we also have the inverse Weibull, introduced in 1982. Another method that has been used to construct new PDFs, new densities, is to use the proportional reverse hazard models. It was first introduced by Lehman in 1953 in the context of hypothesis testing. This class of models here is described by this expression here. So basically, if you have a known distribution, for example, if you have here a known CDF, for example, the CDF of exponential distribution or Weibull distribution, you can just exponentiate this this CDF here, and then you get a new CDF F, big F. So some papers here that have presented the, examples of this class of distributions are Gupta and others, 1998. They presented the generalized exponential. It corresponds to this formula here. You just plug the exponential distribution function as your big G function here. If instead of an exponential you use a Weibull, you get here the exponentiated Weibull distribution. Other example of methods for constructing new distributions is to use the inverse probability interval transformation. The basic idea here is that it's very similar to the inverse CDF sampling method. So this method here was deeply discussed in 2006, but we can see some examples of distributions of this class being introduced in previous years. So the basic idea is that you need to combine two CDFs, two distribution functions. For example, if you have here H being a distribution function on the support between 0 and 1, and G is an arbitrary distribution function. If you apply this composition here, you get a new distribution. So this density here corresponds to just taking the G inverse on the unity interval variable here corresponding to H. And we can find many examples of distributions being introduced in the literature that are models from this class of distributions. For example, if your H CDF is just the CDF of the beta distribution, it has to be the distribution between 0 and 1. You get a class of distributions that has been called the beta-generated distributions. And you will see some examples of beta-generated distributions when you combine your beta G with some, the H is the PDF of the beta distribution, and you can try different types of functions G. So for example, if you combine beta with Gumbel, you get the beta Gumbel, obviously. And it has been introduced in 2004. You can also get the beta Weibull, beta generalized exponential, and so on. And then they discovered that you don't need to use beta. You can also use any other distribution between 0 and 1 as your H. So there are a class of distributions called the KWG. It was discussed here, it was introduced in 2011. And some examples have been also introduced in the literature. There are also some papers here that present examples from this class of distribution. The Kuhn-Weibull and the Kuhn-inverse Rayleigh. The later one has been introduced this year. And obviously you can use any other distribution between 0 and 1 as your H function. There is an example here of generalized beta-generated distributions. This is a greater class that includes the previous ones. And probably you will see new examples of of distributions from this class being introduced in the literature in the future. So the question we have here is, okay, we have these distributions, but are they useful? We haven't seen for some of these distributions here, we haven't seen any example of application apart from the paper that introduced the distribution. So we were very curious about trying to compare these different distributions here and see what properties we get in the inference part, because the probability part, the moments and everything else has been covered in the first paper, on those papers here. But we haven't seen the inferential part, either frequentist or Bayesian analysis. So the way we implement our Bayesian analysis here is using an R package called Laplace's daemon. Well, Laplace's daemon has been removed from CRAN, but it's still available on the developer's web page. You can just Google Laplace's daemon, and there's a group of people is still improving this R package here. So the basic idea here behind Laplace's daemon is that it includes dozens of MC algorithms, just from a random walk proposal to adaptive algorithms. You can see a great selection of things to try here. It also includes Laplace approximations and so on. The MC algorithm that we use here is the adaptive metropolis algorithm that has been discussed in this paper here. So here are some details of the implementation here. For each model analyzed, we generate a sample of size 100. So we have tried this several times, trying to get a sample, a reasonably sized sample from each model. And we would like to know how is the estimation from the true model. If we generate from the true model and use the same model to estimate the parameters, how does it behave? So that's our question here. So most of these distributions, they have positive valued parameters, just like the exponential, gamma, and so on. So just for convenience, we transform all the parameters. We reparameterize the parameters using the log transformation, so it's easier to optimize and calculate MLEs and maps estimates. So our set of priors here is just the independent normal priors. Here we have been very arbitrary about the hyperparameters. We have fixed our hyperparameters. So for example, here we set a mean equal to 0 and the variance equal to 4, just to remember that it's on the log scale. So it's going to e to the minus 4 to e to the positive 4. For our results here, we just have generated 200,000 posterior samples. We have a burning of 100,000 samples. So I'm going to show first a very simple model here. a inverse Rayleigh distribution. The density has this form here. It's a one-parameter distribution. So we have estimated these. For example, we generated a hundred samples from this model here, with theta equals to e to the minus 1/2. And then we try to estimate this model here using, for example, maximum likelihood. And we see, this is just one of the examples, but we can see that usually for this simple example here, our maximum likelihood estimates are very close to the true value, and so is the posterior mean and the 95% credible interval. Here on the figure, we have the Kaplan-Meier estimation here for the survival function. Here on the thin line here, we have the point-wise posterior estimate for the survival distribution. We just plug in our posterior estimates into the model survival function, and then we calculate point-wise credible intervals, credible bounds, and the mean estimate here. And we can see that it's very close to the Kaplan-Meier estimate. And here is one example of very complex model here. This is the beta generalized exponential distribution. It has 4 parameters. So it has this complex form here. This is a complex function of A, B, lambda, and alpha. So what we have seen here is that, just let me show the estimates. The estimates here are terrible. For example, first thing we had tried is just to do maximum likelihood estimation. And when we did that, we saw that, for example, for some data sets, we get estimates that are close to the true values. For other data sets, for other 100 generated samples, we see that the maximum likelihood estimate goes to infinity. So we saw, for example, that if we try to analyze the shape of the likelihood function, we see that, for example, if we fix some of the parameters, if we look at the profile likelihood, we can see that sometimes, depending on the data set, the likelihood is a monotonically increasing function of the parameters. So, for example, it has a flat behavior going to infinity. So when we try to do the optimization is just not so good. The algorithm stops at the tolerance criteria. But if we look at the shape of the function, we see that there is no maximum. The maximum is at infinity. We thought that we could solve this problem if we assign a informative prior to the parameters, and then if we have a likelihood function that is monotonically increasing, and we combine it with informative prior, we will get something that is proper as our posterior distribution. For our example here, we couldn't think of, well, we are just working on simulated examples here, so we don't have an idea of what would be an informative prior here. So in this case, we can also see that the posterior mean estimates are also terrible, even if we generate from the model we are estimating. So just my final remarks here. We saw that for some of these functions here, if we look at the likelihood function, it's a very complex function of our parameters here, so we will need more time to think about how to solve this problem and how to evaluate the most complex functions here during estimation. We saw that both MLE and the posterior summaries suffer from this problem, and as our further steps, we would like to analyze these models, at least try to tell which models are best for estimation, which models we would say that are useful, and try to combine them with linear predictors and censored data set. Okay, thank you very much.